Now, if you take a look at these two terms, you can use comparing of the coefficients, because you can, this side it would have like 0 times x to the power of r minus 1 plus 0 times x to the power of n plus 1 r minus 1, right? So we comparing the coefficient. For the first one, we would get 4a0 times r minus 1 plus 6a0r is equal to 0. From that, a0 cancel out, so you would get 2r times r minus 1 plus 3r equal to 0. This one is an indivisible equation. I mean, if you don't use the formula from the beginning and you just derive it down, you would get the indivisible equation. Finally, you would get the indivisible equation. You don't need to find P0 or Q0. You just derive it down here. You would end up with the indivisible equation. From that, you can find the value of r. But now we already know because we use the formula. So like I mentioned for you from the beginning, that you can use this formula, or else you can just go derive by the process of, combining the terms, and then you would end up with the indivisible equation. And with this term, you would get the recurrence relation, right? Because the term in the parentheses is equal to 0, right? And then it got to starting from n equal to 1 until infinity. So you shouldn't forget to write this condition down, because it's not starting from 0, it's starting from 1. How do I know that it's starting from 1? Because the summation there is starting from n equal to 1 into the infinity. And from there, I can write down an as a function of an minus 1 as my recurrence relation. Now, we got the value of r. So you would get two sets of an as a function of an minus 1. The first set is by replacing r equal to 0. And the second set is by replacing r is equal to minus 1 over 2. Right? And the set which is r is equal to 0 would go to your first solution, which is y1 is equal to n times n minus n0 to the power of n plus r1. And the second set would go to your y2, which is the value of dn. Now, we put r equal to 0 into our recurrence relation. We would get an is equal to an minus 1 divided by 4n times n minus 1 plus 6n. Which is, if you combine them together and rewrite it again, you would get an minus 1 times 2n plus 1, where n is greater than 1. And then, like I said, you've got to replace n equal to 1, to 2, to 3, to 4 to see that whether they have a sequence of the number or it's just a random number. If you plug n equal to 1, you would get a0, right? Divided by 2 times 4, 2 times 3. And then if you plug n is equal to 2, you would get a1 divided by 4 times 5. If you plug the value of n equal to 3 there, you would get a3 is equal to a2 times divided by 6 times 7. Now, take a look at your a2. You know that your a2 is related to a1, so you plug the value of a1 in there. You would get a0 divided by 2 times 4 times 4 2 times 3 times 4 times 5, which is 5 factorial. So now you know that it is in the rhythm of your factorial. So now this term, 2 and 3, 2 times 3 equal to 3 factorial. 5 times 4 times 3 factorial equal to 5 factorial. 7 times 6 times 5 factorial equal to 7 factorial. So that means if you plug the value of an there, you would get a0 times divided by 2n plus 1 factorial, right? Right? Because if you put n equal to 1, you would get a1 equal to 0 divided by 3 factorial. If you put a equal to 2 there, you would get a0 divided by 5 factorial. If you put the number of 3 there, you would get a3 equal to a0 divided by 7 factorial, which is correct. Then you can write down the solution of your y1. Your y1 equal to summation of an x to the power n, because your r1 is equal to 0 and your s0 equal to 0. So this one you would get a0 plus a1x plus a2x squared plus a3x to the power 3 plus a4x to the power 4 until infinity. And now you're going to plug the value of a1, a2, a3 there, because all of them in the form of a0. You would get a0 plus a0 divided by 3 factorial x plus a0 times 5 factorial x squared, and so on. You take a0 out, you would get this term. And then we know the function of hyperbolic sine. So we try to rearrange in such a way that we got the function that we usually know. Okay, so I just saying that, okay, I'll put the x squared in there. If I want to put x squared there, I got to divide it by x squared. Because with this rhythm, we can get the exponential of, the sine hyperbolic of the square root x. Okay, this one is just the way to rearrange into the function that we know. Just that. But in the exam, if you write down this, I think it's okay. If you don't know the function, I'm not really concerned. I just want to know that whether you understand the method to find the solution. But at the end, if you want to, even though your power series is fitting with any function, but if you don't write down, that's fine. Okay. Now for our second solution, we just replace r is equal to minus 1 over 2 to get another Lagrange relation. And from that, I would put it as a star, because if I put it as a an, we're just getting confused with the first case. You would get an again, so I would put it as a an star, or you can put it as a bn equal to bn minus 1 divided by 4 times n minus 1 over 2 times n minus 1 over 2 minus 1 plus 6 times n minus 1 over 2. That's fine. Okay. You can put it as a b, or you can put it as a star in order to make it different from the first case. And from that, I've said that I would get an star is equal to an star of n minus 1 divided by 2n times 2n minus 1, which is different from the first case, right? The first case is not in this form. The first case is in the form of 2n, an minus 1 divided by 2n times 2n plus 1. Now this is become 2n minus 1. This term is different. And then it's just like the value of n equal to 1 there, n equal to 2, n equal to 3. We got A0 star divided by 2 factorial for A1 star, and A2 star is equal to A0 star divided by 4 factorial, and then plug n is equal to 3 there, you would get A3 star equal to A0 divided by 6 factorial, and so on.